All right, thank you so much. I hope everyone can hear me okay. He said that you should all rate this afterwards, so I presume they're gonna build a Rexus on top of that. And if they don't, it's an opportunity for y'all. As you mentioned, I'm gonna talk about composition today. For some of you in the room, you've already realized that this is a category theory talk and you're looking for the door. But don't worry, because it's not actually. So let's start with the definition. So what is composition? Compositionality, or Frege's principle, says that the meaning of a complex expression is determined by the meanings of its constituent parts and the rules for how those parts are combined. So I'll give you a minute to digest. So complicated things are made out of Legos, and we really care about how those Legos can be put together. If you're an old school Lego fan, you put them together by putting the studs into the holes. If you're a more modern Lego fan, you know about things like snot. You know about things like illegal building techniques. But all in all, what's important for a Lego builder is to know how to put the pieces together. I claim that most of machine learning, especially these days, is becoming more and more like this. It's more and more about knowing the constituent parts and explicitly knowing which parts can be put into one another. Down here in the corner, I teach you how to make a lemon meringue pie. For those of you that may be your best takeaway from this talk, let me know, that's fine. I'm okay with that. This is an example that I really love from Fong and Spivak, and that is a category theory book, but that will be the last thing I say about category theory. But like, why? Why waste anyone's time talking about compositionality? It's so obvious, it's almost trite. So let's look at some machine learning examples. I'm a very example-driven person, and so let's talk about some. Let's start with matrix factorization. My guess is that a lot of you are familiar with matrix factorization. Some of you might be familiar with it in the sense of embedding models, in particular for latent factor models for recommendations. In those sorts of models, we start out by saying, we claim there's a matrix out there, and that matrix represents users and items. And the elements of that matrix are these little RUIs. They're the ratings. If this is new to you, don't be too worried. Just take the rows of a matrix to be users, the columns to be items, and fill in every element or cell that you know about with the rating between that user and item. Now, some of you might already know that this matrix is not dense for almost every application in the real world. If it were, recommendation systems would be a boring problem. But more importantly, that would mean that you've seen everything out there. There's no recommendation system if you've already consumed all the content, if all the items are known to you, and you've got opinions on them. Remember, every RUI is an opinion. So what do we do in matrix factorization? Well, in matrix factorization, we claim that there's some existential matrix out there in the universe that we're not privy to, and we'd like to approximate it. And how do we approximate it? We approximate it through an iterative process, usually trying to learn a matrix decomposition into 3 pieces. We often talk about singular value decomposition. There's some technical math details on why we think U should be the type that it is and why the middle matrix should be diagonal and the last one should also be of this particular shape. But actually, I don't want to get too much into the details of this factorization. I'd actually rather you focus on the picture in the bottom corner. What is the picture in the bottom corner saying? It's saying that these 3 matrices compose. And in particular, this very squeaky stage is reminding me that their composition is a shear and a translation or rotation, and then another shear, and that any general matrix of a certain type is just these 3 things in a row. When I was taking linear algebra, this was a very amazing geometric fact. But now that I do machine learning and I think about this for recommendation systems, why on God's earth do I care? Well, the first reason I care is because that first matrix actually tells me a correlation structure between the users and something that I can't see or know. And the last matrix tells me a correlation structure between the items and something else that I can't see or know. And the special, amazing, beautiful fact is that those two things that I can't see or know are the same things. Those are the latent factors, and thus we get an embedding. And again, like, I'm not going to go too deep into the mathematics of this, but this is really interesting because I started out with just sort of this like linear algebraic observation. It turns out to be really useful for actual machine learning. And it's just composition. The constituent parts are metric embeddings, and how they are combined is linear algebraically. In this type, matrix multiplication. Now, this is probably not much of a surprise to most of you. So I don't claim to be saying anything new. And so rather than try to impress you, I'll say something even more obvious. Let's talk about seasonal average pooling for time series. So some of you may have played with some time series before. Some of you may have tried to do some forecasting in your life. Sometimes people come and they say, what's the simplest forecasting model you can build? And this is one of the ones that I think is the simplest one out there. And the reason is because it's this very basic idea done over and over in layers that builds up a ridiculously good forecast for a lot of forecasting problems. I've seen this beat Surima time and time again. I've seen this beat Fourier modes time and time again. This model, which I'm about to say, is basically trivial mathematically, even though it's got a boatload of symbols on the left-hand side. So what is it? Well, it does the following. It says, you know, what's the average this year and last year of the value of the time series? So let's assume we're trying to predict the value of the time series moving forward in time. And so I take the last 2 years or 3 years or 4 years, and I say, what was the average each year? What was the average of 2020? What was the average of 2019? Take those. Each of those averages is a number by year. Let me try again. Take the average by month in those previous years. Apologies for the error. Take the average by month in those previous years, and now you have an average each and every month of the year over the previous time series. And so now you have a prediction in the future months, each of those months, what that average would be. So this is average pooling at the layer of month per year. Notice here that in symbols, this is really just looking at the indicator function of which month of the year you're looking at, taking the average, and then just taking that as your prediction. So if I just took that prediction in 2021, what I would say is January has a prediction, February has a different prediction, and these are just the previous Januaries and Februaries of previous years. So now what I'm gonna do is I'm gonna take the error or the residuals. I take those residuals and I do the same process for week of month. I've already done month of year, so I've already learned all I can from these averages. Let's just do week of month now. I do the same thing. Remember, I'm now fitting to the residuals. This is important. I do the same thing. At the end, I now have a prediction for the residuals moving forward in time. I sum those together with my previous model. So now I've taken a prediction for the residuals plus the prediction for the baseline, and I have a little model for every week of the next year. And then I'm gonna do it one more time for day of the week. Again, on the residual residuals, I'm gonna sum all these up at the end. And what have I gotten? I've gotten a forecast for every day of the year built purely from average pooling. On the right-hand side is a real demand signal from a real company, and these are the real residuals. And this has been benchmarked against several high technologically advanced forecasting methods, and this beat them all. Okay, what are the constituent parts? They're the pooling layers. How are they combined? Recursive residual additive processes. Now, this is about the time in the semester when I teach my students where they're starting to see another recursive residual additive process. Can anyone think back to their ML education and tell me another model type that uses this kind of sort of process? It's not a time series, but it's the same, sorry? I mean, you can technically use it in NLP too, but I'm thinking of a particular model type. Boosting, someone said boosting. This is boosting, right? I cheated. I did boosting without all the fun. Okay, let's talk about boosted trees. All right, so some of you are probably like, man, I won a Kaggle competition once with a boosted tree. Great, love it. Because boosted trees are the same idea. You basically train your sample, you fit some simple model, you take the residuals, you fit a simple model, you take the residuals, you fit a simple model, etc. And what do we get at the end? We get an extremely powerful learner, don't we? We've seen time and time again that this method, frankly, kicks. So, okay. Well, the constituent parts are weighted learners now. Ooh, that's fun. They're weighted. And how are they added? They're recursively, again, recursively additive from the residuals. Okay. Before we move on, though, I do want to take an extra minute here and talk about this weighted word. Are we excited? Should we be excited? The whole world's excited about differential learning. We should be excited, okay? Because this means that there's additional model parameters to tune. Heck yeah. So now we've got composition, and we've got like tunable model parameters. I swear to God, there's other model types that do this sort of thing. Yep. So neural nets, if you've heard of them, they like to build out of pieces. They like to compose things together. They like to use weighted components. And these days, a lot of people are very excited about foundational models. Why are we so excited about foundational models? Well, one, because it saves you on compute. You can let the big people do their fun, and then you can come along and use those foundational models to train from. One of my favorite papers I've seen recently is this paper that I'm stealing the diagram from on the right and it's cited in the corner. Is like basically there's so many ways to use a foundational model. Just because you're starting with a pre-trained network with pre-trained parameters and you're going to start on your task, there's actually so many directions to go. You can do fine tuning, you can do joint training, multitask learning. I'm going to talk more about that in a little bit. But what's the key idea here? The key idea here is that these are the Legos. And we're starting to understand what the studs and what the holes are. We're starting to recognize that like plugging a thing in, okay? And by now, I think the important thing, ooh, I got some feedback, sorry. The important thing I think that you might care about, or at least I find really exciting in this picture, is actually this loss function down at the bottom. I've already kind of moved on from the excitement about plugging a thing into a thing, and I'm already starting to think about this like loss. Because now my loss is over the whole network. It's kind of this like meta step for learning. And that starts to get really exciting. So we'll play the game. Constituent parts are the parameters trained via learning. How they're combined is layer composition and loss sharing. So this is where we start up in the ante again. And so some of you might think like, okay, he's managed to get us all the way to like modern times. What's next? What's on the next slide? Anyone want to take a guess? All right. Some of you are less nerdy than me, apparently. So globally natural deep learning. Have any of you heard of equivariant deep learning? We're skipping right past equivariant and moving on to globally natural. So equivariant deep learning says that there's inherent symmetries in your data. And the more that you understand those inherent symmetries in your data, the more you can exploit parameter sharing and even fancier tricks than that. Well, I don't have time for equivariant, so I went straight on to global natural. Global natural is basically, I think of it as a toy, but at the moment I think of it as a toy, but I think it's a really cool idea. It's basically saying that like you can do this equivariance up to sort of weaker definitions of symmetry. So mathematicians love to say, oh, there's a symmetry, and we can exploit that symmetry to learn things via like Netter's theorem. Cool. Well, then mathematicians come along and say, look, I don't care about exact equivalence, I care about pseudo equivalence. Let's play the whole symmetry game, but for pseudo equivalence. And so that's what this stuff is about. This is really modern work. Haven't seen any applications of it, but it's fun. And what is it? This is very overtly composition. These are the action mappings on the data structures and the function composition and kernel convolution. So, okay, so that's a bunch of types of machine learning. And, you know, I've managed to bully all these things into the box of composition. And maybe it was somewhat convincing. But like, maybe these are all too theoretical. Maybe your point is that like, okay, well, like learn that in your machine learning classes and read the papers, you know, during the week and do the coding to make money. And that's fine. Because actually, I think composition is really important for the tools that you use and the way that you think about your models in general. I actually think that if you stop at just the models alone, you're missing the point. So what if I told you that I wanted to sell you an ML pipeline? I'm some company and I want to sell you an ML pipeline for your task. And I tell you that this pipeline is comprised of pure components, okay, in the functional sense. So they always return the same output and they have no side effects. It's a higher order. They're higher order components. So you have APIs for all the functions. And they return those APIs as methods. They're composable, seems relevant for the talk. And they're queryable, which means that a fixed set of parameters and inputs allows you to create the entire pipeline start to finish. Cool. Some of you are probably now very afraid this is turning into a functional programming talk. Some of you from the more DevOpsy side might be thinking like, I think I saw a microservices talk one time that talked about this. But what about MLOps? Can we have some fun too? I claim we can, because the components of an ML pipeline should probably also do these things. One example I really like is fklearn. So recently, and by recently I mean earlier this year, this person, who you've probably heard of, Andrew Ng, has been proselytizing an idea of a data-centric approach to AI. In particular, he recognizes the effectiveness of data improvement and preparation and a very careful attention to the data that your product is built on. I think he rightly identifies that one formulation of the data pipeline is as follows. You scope the project, you collect the data, you train the model, you deploy in production, you realize that you need to fix your data. You go back, you look at your data, you train your model, you deploy in production, you realize that the way you trained your model wasn't appropriate for the task, you go back. And I think that's awesome. I really like this framing. But in his talk, Andrew Ng says that we should move from a model-focused AI to a data-focused AI. He has a lot of good reasons for this, but ultimately, I disagree. His recommendation is that you don't hold the data fixed and that you should not hold the data fixed and iteratively improve the model. His claim, which is interesting, is you hold the code fixed and iteratively improve the data. He gives lots of really important and amazing examples of sort of bad labels. Recently, there was a really cool paper about bad labels. If you haven't heard of it, you should go look for it. I think this is super useful, but I think it's thinking a little bit too small, actually. I think you should be modular and flexible, but I think you should hold the composition fixed and iteratively improve one component. Why is it always that the data is going to be the thing that's going to improve things? We've seen over and over and over again that changing the loss function can dramatically impact the performance on a task. Through neural networks, we've seen that changing the architecture and the way those things are combined absolutely changes the game in some cases. I think it's almost silly to claim that we would ever get the model right on the first try and simply need to improve the data. or that we've gotten the deployment right on the first try, and we simply need to fix up the model. How many times have you deployed a model into production and then later said, you know what, I didn't really build a feature store for this because I didn't need it, but now that I'm in production, I realized actually cold starting sucks. So I should probably build a feature store and have a low pass path to deal with cold start. So a little spicy, but I think we should be looking at a pipeline-centric AI. The other components change just as much. And I think your expectations for what your model does, your objective functions, the sources. And I think it's really cool to say, like, don't obsess on the model development. The model development doesn't need to be the product. The product should really come back to the data and your understanding of the data. But I think it's also silly to not think about the way that all these pieces plug together. One of the things that you get for free is this allows you to optimize and improve and iterate on any component when it's the lowest hanging fruit. When we talk about optimization in a more mathematical context, we always talk about greed. You can be greedy with your model pipeline creation. You can say, what's the easiest problem to solve right now? I'll go solve that. Does it improve the performance of my model or my pipeline rather? Cool. Seems worth it. And so now I want to bring in yet another buzzword, which is this data flywheel. This is a thing that I hear every couple of years. I feel like is like the new idea. And it's this idea that you like build a cool thing, users get excited, they give you data, you learn from that data to make a better thing, and then you show that to your users. And it's a flywheel. And actually, I think it's a really like natural and reasonable thing. But like, can you imagine if this flywheel had one of the arrows broken? Or if this wheel was trying to roll over a very large rock? It wouldn't fly. The whole idea of a flywheel is like energy conservation and sort of inertia. Well, you don't have any inertia if you don't have composition. All the arrows in this picture are really talking about composition. And one thing that you should notice here is in this case, you have a cycle in your composition graph. Now I want to talk about one specific application of this architecture. And this is absolutely the best diagram I've seen this year. This is by Carl Higley. And I just absolutely love this picture because it takes the concept of recommendation systems, which is like pretty hard and involves a lot of moving pieces. And in one picture, you can actually like, you could train an army of 100 data scientists to work on this one picture, or you could have one. And I think anything that scales that well as a framework or a methodology is something to really pay attention to. So I'm a really big fan of this architecture. And I won't go into all the little bubbles and diagrams and arrows, but the thing that I want to draw attention to, and by the way, this is also like a sort of a remix of something by Eugene Yan, who writes really incredible stuff about ML in production. I want to make sure I shout that out too, because phenomenal writer. But one of the things Eugene did in his first version of this is he broke it up into offline and online, and then he broke it up into these sort of pieces. In Eugene's original one, it was roughly retrieval, scoring, and ordering. And if you've worked in recommendation systems, you'll probably already understand why those are the right pieces. But if you don't work in recommendation systems, I'm actually more interested in what you think when you look at this picture. Because when I look at this picture, I see, okay, retrieval, cool. That's like hardcore infra stuff. Okay, I kind of know what's going on there. Then filtering also feels like retrieval or infra stuff. Ranking, okay, now we're doing some machine learning. That's cool. And then ordering, you might see some business logic plus modeling going on here. But then you start looking at the components and you see how every single one of these can be started out by a SQL query and over time be evolved into a really interesting embedding model with vector search and things like that. And so what I love about this is just how much it scales, how both clear and broad the scope is in this picture. And of course, I love how compositional it is. Every single thing is a component. Every single interface is either explicitly talked about what the composition rule is, or you can quickly imagine it. And you can go and look up every single item in this diagram and understand why it's a composition. So is there anything that can help to do composition? Well, we're starting to see technology be built up around composition, components of data pipelines. People are starting to talk about coherence and why coherence matters in these pipelines. Shreya writes really incredible open source packages for MLOps and talks a lot about MLOps on Twitter. I'm a really big fan of Shreya's ideas and the way she presents them. And some of us are building these platforms with this very much in mind, specifically baked into the whole idea of what we're building, taking things like data set management, experimentation, optimization, model registry, model CI/CD, and production monitoring, and saying, whoa, 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 those are all individual components. How do we stitch them together? What is the sort of backbone that you need to make those coherence expectations work out? How do you integrate those things into something that a human can use, not simply a mathematician? What does this look like in practice? DAGs like this. And you might say, please don't make me define a DAG like this. I won't. This is automatically generated. This is automatically generated by merely giving the types of components and the way that they interact in the general order that they should. This allows for cyclic DAGs. This allows for, which I know is a little bit of a oxymoron. Didn't realize until I said it. But it allows for sort of like these general architectures of ML pipelines to be built out of simple components. One thing that I find really inspiring is this idea from OpenAI when they were working on Dota 2. They came up with this idea of model surgery. So they train their model to get the best performance they can. They start to see issues, and then they go in, they take the model pre-trained up until that moment as their starting place, and then they start performing model surgery. They change the loss function, they change the architecture, they change the downstream task, and they were performing approximately 1 surgery per 2 weeks. An analogy here is if your dog hasn't learned to catch a Frisbee by the time they're 6 weeks old, don't get a new dog, just like try a different training method. I really like this because without composable tools, this sort of model surgery is a major pain in the butt. On the complete opposite end of the spectrum, Andrei Karpathy in 2019 at ICML talked about how they were doing explicitly not model surgery because they got themselves into situations like this, where they had written down on scratch paper what were the hashes of their models that they were using. So that brings us to the last point. So you've got all these components, you've got all the ways that they interact. We've seen that everything from the models themselves to the way that they fit into a deployed production architecture can all be instrumented through composability. What about the people that work on these things? So it's hard to build a team architecture that enables people to do their best work and create opportunities for growth. Sometimes these things feel at odds even. I've been on both sides. So how do you create robustness to team departures and vacations and burnout? Well, some of the same things that we talked about before, swapping things in and out, understanding very clearly the interfaces between things, and coherence, turns out can be a really convenient way to structure your team. I also think that data science and ML doesn't steal enough from engineering, despite how much we already do. And I think things like atomic tasks and assignee agnostic tasks PR processes and component expertise are things that we can all learn from engineering. They do really well. So when it's time to work on model development, there's a ticket for that. It's clear what the goals are, who's going to work on it, who's available and interested. What's the process of getting that work reviewed and pulled into the rest of the process? Well, it's a PR process. Maybe you share it through a reproducible report. And what about component expertise? Everybody should really have one thing that they are the expert on, but you shouldn't have sole ownership. Main reason is because, if you are brought up in the tradition of full stack data science, it sounds great for a while, but what I experienced is that over time that stack will own you. And your entire job is essentially maintenance. There's not a lot of room for iteration and advancement when you're kind of spending most of your time working on aspects of the stack that are so outside of your knowledge base, and you've learned just enough to kind of make them work. And then when we're talking about composition, we've stressed over and over and over that the arrows are really what matter. And I think there's probably more talks about teams and tech about relationships than I could possibly count in a lifetime. But I'll still take this opportunity to remind you all that understanding the relationships between people and understanding the relationships between people's work is ultimately more important than almost anything else. When it comes time for someone else to take over your work or collaborate with you, having a clear understanding of what's been done, what were the inputs and the outputs, is going to make that a lot faster. Having onboarded into teams in both scenarios, I've experienced how difficult it can be to cold start. And I'll leave you with one more Karpathy reference. In that same talk, he also addressed the challenge of having a massively multitask training system, and how he wanted all these people to be able to individually work on the individual tasks and components of the system. But even beyond the sort of like human frictions, there was just the difficulty of like, how do you understand what changes are being made? And I think 2 years ago, it was a little harder, but these days with things like reproducible reports and MLOps tooling, we've gotten to a better place.